The ratio of energy of the first excited state E1 of a particle in 3 dimension box of side L and L by 2. This question is incomplete here. To the ground state E0 of a particle in 3 dimension rectangular box is this. Solution for this: the energy of a particle confined in a rectangular box is A and X and Y and Z is equals to pi square by 2m nx square by lx square plus square by ly square plus n square z by lz square. The ground state and first excited state for excited state energy for the particle are E11 would be pi square h square by 2 m 1 by l square plus 1 by l square plus 1 by l by 2 square equals to 6 pi square h square by 2 ml square. E21 would be h square pi square 2m 2 square l square plus 1 by l square plus 1 by l by 2 square equals to 9 pi square h square by 2 ml square. This state is degenerate. That means same energy we can get it with this. So where we have used Lx is equals to L, Ly is equals to L and Lz is equals to L by 2. The ratio of the energy of the first excited state E1 to that of the ground state E0 of a particle is that is E0 can be written as E1. E1 by E0 is equals to 9 pi square h square by 2 ml square into 6 pi square h square by 2 ml square equals to 9 ratio 6 equals to 3 ratio 2. Thus our answer is A. Option A is correct. If Li are the component of angular momentum operator, then commutator equals to, we have to determine the value of this commutator. Let us compute the value of commutator in the following manner. Summation I is equals to 1 to 3 Li Li is equals to commutator L into L1 plus commutator L into L2 plus L into L3 to L3. I cap, J cap, K cap, where L is defined as L is equals to I L1 plus J L2 plus K L3. Let us evaluate the value of first commutator. That is L cross L1 into L1. So we would be having it minus J cap L3 plus K cap L2 into L1, which can be written as minus J cap L3 L1 plus K cap L2 L1. So this gives a result minus J L2 plus minus K L3, where we have used I L1 plus J plus K L3 L1 equals to I cap L1 plus J cap L2 L1 plus K cap 3 L1 is equals to minus J cap L3 plus K cap L2. Similarly, for second and third commutator, we have L2 to minus I cap L1 L3 equals to L3 I cap L1 minus I cap L1 plus minus K cap L3 minus I cap L1 J cap L2. Thus, the commutator L vector Li is equals to minus 2I L1 minus 2J cap L2 minus 2K cap L3 equals to minus 2L cap. Thus our option. So let us check our option. None of the options are matching it. Still, if according to me there was the option should be minus 2L. So you can mention it in your, you can mention that or remember that there is a mistake in this question. Not question but an option. This problem is related with the translation operator, and we have discussed in detail about the translational operator in CSIR December 2019 paper. So I request you to go through the video of December 2019 problem of quantum mechanics for detailed explanation. Here I am just using its result. So in this, the wave function of a particle in one dimension is denoted by psi x in the coordinate represented by this. If the action of t psi x, we know it that translation operator in general is defined as t to the power minus I AP by h cut. So when t is operated on psi x, it resulted into an eigenvalue psi x plus a. If t is having a form IAP by h cut and t operated on psi x, then that gives us psi x minus a. That means we can say t operated on psi x would give us psi x plus minus plus a, or I would be simply writing it like this: e to the power minus plus IAP by h cut operating on psi x would give us psi x plus minus a with eigenvalues x plus minus a. Thus, if t operate on phi p, we would be having e to the power minus IAP by h cut phi p. And that can also be represented in p plus a. So for this problem, our option B is correct. I have not discussed about detailed explanation of translation operator. Again, I am saying it. Please watch the video of CSIR December 2019. A particle moves in one dimension in the potential V is equals to half kT x square, where kT is time dependent parameter. Then the del by del t V, the rate of change of the expectation value V of the potential energy is. Solution. The rate of change of an operator A is given by del t operator A equals to 1 by iota h cup. The commutator of operator A with Hamiltonian h plus del by del t of operator A. Substituting the value of operator A, so del by del t V equals to 1 by I h cut V commutator h plus del by del t of expectation value of V equals to 1 by I h cut half kt x square plus p square by twice m plus half kt x square plus del by del t of half kt x square. So we would be having it 1 by I h cross 1 by 2 kt x square p square by 2m a commutator plus half kt x square into half kt x square in commutator plus 1 by 2 average x square would come out, and here you will be having del by del t k into t. Now the value of this commutator vanishes out, and here we would be having it 1 by I h cross 1 by 4 kt by m x square p square plus half average x square into del by del t k of t dk by dt. The value of this term would be 1 by I h cross 1 kt by 4m, and this term would be 2xp plus px, and here this is in expectation into IH cross plus half x square dk of t by dt. So IH cross to IH 2 से 2, so our answer will be kt by 2m expectation xp plus px plus half x square del kt by dt. Now commutator of xp, I have written it, so I am writing it directly here. twice xp plus px into IH cross. So thus our option A is correct. This problem is related to scattering, quantum scattering. Here, the differential cross-section for scattering by a target is given by d sigma by del omega theta phi a square plus b square cos square theta. If n is the flux of the incoming particle, the number of particles scattered per unit time is. So we have to determine the number of particles. Now, solution. We have del sigma by del omega theta phi is equals to a square plus b square cos square theta. Now, the number of scattered particle is given by del n by del omega equals to n into f theta phi mod square. So, the total number of particle is given by scattered per unit time is given by dn integration and d sigma by omega into del omega. That means n 0 to pi 0 to 2 pi a square plus b square cos square theta sin theta d theta d phi is equals to 2 and pi 0 to pi a square sin theta d theta plus b square cos square theta sin theta d theta 0 to pi equals to 2 pi n into 2a square plus b square 2b square by 3 equals to 4 pi n a square plus b square by 3, where we have used integration 0 to pi by 2 cos square theta sin theta d theta is equals to 1 by 3. Thus, our option D is correct. A particle of mass m is in potential V is equals to 1 by 2 m omega square x square, where omega is a constant. Let A is a dagger operator m omega 2h cross x cap plus ip m omega. In the Heisenberg picture, del A by del T is given by. So, solution. The Hamiltonian of particle in harmonic potential in terms of ladder operator is expressed as H is equals to H cross omega A dagger A plus 1 by 2. The time evolution one observable according to Heisenberg equation is del A by del T equals to 1 by IH cross A H equals to 1 by IH cross A into H cross omega A dagger plus 1 by 2, which give us 1 by H cross omega into A dagger, which gives us minus omega. Here I made a mistake that A dagger. So that would be minus I omega A. Bracket where we have A dagger A is equals to A dagger A commutator of A plus A dagger into A, which is equals to A. Thus, our option minus I omega A is correct for this problem. This problem is related to the relativistic quantum mechanics. Here, Dirac Hamiltonian for an electron corresponding to a classical relation is given. The classical energy momentum relation for a particle of a charge q in electromagnetic field is. Here, this question is incomplete as one important relation is also given in the question, that is C square P minus Q by C A square plus M square C की power 4. So, the classical momentum energy relation for electromagnetic potential is, ठीक है? So that relation is also given in the question. Therefore, the Dirac Hamiltonian on question, there is a problem in the question. Here the question, I would be writing it the question from here. The question is saying the classical energy momentum relation electromagnetic potential phi A is E minus Q phi is equal to C square P minus Q by C A square plus M square C की power 4. Therefore, the Dirac Hamiltonian for an electron in an electromagnetic field So this is the complete questions. Now its solution would be, so Dirac Hamiltonian for an electron EM field is H is equals to C dot P plus E by C minus E phi, where we have used Q is equals to minus E. Thus, our option D is correct. A particle of energy E is scattered of a repulsive spherical potential defined by VR is equals to this. V naught for R less than a 0 for R greater than equals to A, where V naught and A are positive constants in the low energy limit, though total scattering cross section is 4 pi A square 1 by K A tan K A minus 1, where K square is equals to 2m by H cross square V naught minus E. In the limit V naught tends to infinity, the ratio of sigma to classical scattering of a sphere of radius A is. So here we have to determine the ratio of sigma total by sigma classical scattering. The total is total scattering sigma t is given by sigma t is equals to 4 pi A square tan Ka by Ka minus 1 square, where K square is equals to 2m H cross square V0 minus E. In the low energy limit V naught tends to infinity implies K tends to infinity. So the first term would vanish out in the limit V naught tends to infinity. It behaves like a hard sphere. The total scattering cross section becomes this sigma t is equals to 4 pi A square. The geometric cross section area of the particle is mass Cs is equals to pi A square ratio of to the classical scattering cross section of a sphere of radius A is sigma t by sigma Cs is equals to 4 pi a square by pi a square equals to 4. Thus, the correct answer is option A, 4.